Welcome to all. Our today's topic is torsion of circular shafts. This is a circular shaft with diameter d and length L and subjected to a twisting moment T. T is twisting moment. Or torsional moment, or you can say torsional moment. So until this we have studied stresses due to axial loading. What was axial loading? Axial loading was like this. Say this was the shaft, then axial loading load was subjected to along the axis. Now this is a new type of loading which is torsion. That is, say this is the fixed end of the shaft and here a twisting moment is subjected which tends to rotate the free end of the shaft. So this is called twisting moment or torsional moment. If we draw the free body diagram of the shaft, then the free body diagram will be like this. So this is the torsional moment and here this is the reaction moment. So this is the free body diagram. This is the free body diagram. Now let us consider one shaft with diameter d. This is the shaft. So this is end A and this is end B. End B, A is fixed. This is fixed end and this is free end. So this is one circular shaft with diameter d and length L. Length of the shaft is L. And this shaft is subjected to a twisting moment or torsional moment T at the free end B. Now, due to this moment, what will be the deformation of the shaft? How it will deform? That is, the free end, say on a free end, this point was A and this point A will move to A prime. That is, if we draw the sectional view of the free end, that is, say this was point A which moves to A prime, that is, this is my A prime, and this rotation, say this amount of rotation is theta. So theta is called angle of twist. So theta is called angle of twist. So due to torsion, the free end of the shaft is rotated and this angle theta is called angle of twist. And from the definition of shear strain, you can understand that this angle is nothing but shear strain gamma. So this angle is nothing but shear strain gamma. So from the geometry, what we will get, A prime is what? If radius of the shaft is r, then A prime is L into gamma, that is also equal to r into theta. That is, gamma shear strain is r by L into theta. Gamma is shear strain. Shear strain. Now we can understand from this equation, that is, shear strain is maximum at the surface. So from this expression we can understand that shear strain is maximum at the surface, that is where radius is r. So alternatively we can write that is maximum shear strain is r by L into theta. R by L into theta. R by L into theta. And generalized expression, that is shear strain at anywhere, say any radius rho L by theta. So this is for first one is for maximum shear strain, that is at surface layer at any radius rho, say any radius here rho is any radius. The value of shear strain is rho by L into theta. Now if we apply the Hooke's law for shear, that is tau is G into gamma, that is tau max is G into gamma max, which is at surface, that is expression of tau max is G r theta by L, and normal at tau at anywhere, shear stress at anywhere is G rho theta by L. Sorry, that is tau is G theta by L into rho. That is shear stress is directly proportional to the radius. That is what will be the distribution of shear stress. So shear stress is distributed like this. So here tau max, that is at at radius r, so this is at radius r is the radius, this is also tau max, and at any radius rho, say any radius rho, here tau is G theta by L into rho. So here it is tau, that radius is rho. So this is the distribution of shear stress. Now let us try to determine a relationship between twisting moment T, tau and angle of twist theta. To do that, let us draw the shear stress distribution on the shaft further. So this is the shaft with diameter D, and this is the shear stress distribution. So at the surface, shear stress is maximum, that is at radius r. So radius of the shaft is r. At radius r, shear stress is tau max. And at any radius, say at any radius rho, this is rho, shear stress here, this is the shear stress tau is G into theta by L into rho. So here shear stress at any radius rho is G into theta by L into rho. Now let us take a small strip. Let us take a small elemental strip at radius rho, and thickness of the strip is d rho. Then elemental shear force dF on the element, on the small element, will be what? Tau into dA, that is the elemental area. dA is the elemental area, that is tau 2 pi rho d rho. 2 pi rho into d rho is the area. So this is the elemental shear force. Now elemental twisting moment dt will be 2 pi rho d rho into distance, that is also rho. Now total twisting moment on the shaft T is what? Integral 0 to r tau 2 pi rho d rho into rho. Now let us put the value of tau. Tau is g theta L into rho into 2 pi rho d rho into rho. So T is g theta by L integral 0 to r 2 pi rho d rho elemental area into rho square. Now what is this quantity? This is nothing but polar moment of inertia. This quantity is called polar moment of inertia. That is, this is elemental area 2 pi rho d rho into distance square. That is polar moment of inertia of this small strip, small element. And this is the, if we integral with limit 0 to r, that is total polar moment of inertia. Polar moment of inertia is denoted by J. So that is T is g theta L into J. Now what is the value of J? That is T by J, we can write is g theta by L. This is one relationship. And J, value of J is what? Integral 0 to r 2 pi rho d rho into rho square. Now first of all, let us calculate what is the value of J. That is J is 2 pi rho to the power 4 by 4 integral 0 to r, that is 2 pi r to the power 4 by 4, that is 2 pi r is d by 2 to the power 4 by 4, that is 2 pi d to the power 4 64, that is pi d to the power 4 by 32. So J for solid shaft, polar moment of inertia of solid shaft is pi d to the power 4 by 32. If it is a hollow shaft, say hollow shaft, say for hollow shaft, the stress distribution will be like this. This is hollow shaft. So this is the stress distribution. And for hollow shaft, J will be what? Integral, say diameter here inner diameter is di and outer diameter is do. Then the limit will be di by 2, do by 2, 2 pi rho d rho into rho square, and that will become pi by 32 do to the power 4 minus di to the power 4. So for this is polar moment of inertia for hollow shaft, and we got that the equation we got T by J is g theta by L. Now we have already derived, that is the expression of tau max. What was the expression of tau max? Expression of tau max. This is tau max is, sorry, this is gamma max. Gamma max is R by L into theta. So earlier we get gamma max is R by L into theta. Gamma max is R by L into theta. So what will be tau max? By applying Hooke's law, tau max is GR by L into theta. So this is another relationship, and from this let us write this equation once again. Tau max GRL into theta. So tau max by R is G theta by L. G theta by L. Now let us put a number, say this is equation number 1, T by J G theta by L, and here also tau max by R is G theta by L. So this is equation 2. Now combining equation 1 and 2, what we will get? T by J is G theta by L is tau max by R. Similarly, we can write tau by rho. Tau max by R is also tau by rho. So this is the equation of torsion. This equation is called elastic equation of torsion. And we have made some assumptions, that is material is homogeneous and isotropic, cross section of the shaft is uniform and circular, plane sections remains plane before and after torsion, and last one, loading is within Hooke's law. That is, we have applied Hooke's law here, that is loading is within proportional limit, that is we have applied Hooke's law. Hooke's law is valid. So these are the assumptions I have mentioned earlier for this elastic equation of torsion. Now if a twisting moment is subjected to a shaft, this was the shaft before applying the twisting moment, this was the surface, that is a rectangular surface element, and after deformation the element is deformed like this, and the element is under pure shear. This is the enlarged view of this rectangular element after deformation due to twisting moment T, and the element is under pure shear. So due to torsion, pure shear is the element is subjected to pure shear due to torsion, and this is the enlarged view of the surface element.